Okay, so I wanted to share with you a different way for determining which way a loop of current will rotate when placed in an external magnetic field. And this way is a little bit easier sometimes, I think, for students to understand. And it involves something called the magnetic dipole moment. So I'm going to start off by sketching a current loop. And I'm going to try to make it look kind of three-dimensional. So this is a wire that's kind of coming out towards you. So I'll draw that front part a little bit wider. And then it goes away from you. And then back here, it's looping around. And so somehow we've got current that's flowing around in a loop like this. The magnetic dipole moment is basically going to be a vector quantity, and it's going to be perpendicular to the plane of this loop. So I'm going to draw a dot right in the middle of the loop, and then I'm going to draw a vector, and the symbol for that vector is the mu, which is that Greek letter that we've seen before. Okay, so mu is the magnetic dipole moment. Okay, now to make a long story short, that vector is useful because that vector is going to always try to line up with the external magnetic field. So that's basically what I want you to see. So this will tend to align with external field. And if you can see that, it's actually a pretty easy way to figure out which way a loop will turn if it's put into a field. Okay. So let's define a couple of things here. Mathematically, the magnitude of this vector is going to be equal to, we're going to make it equal to the current flowing through the loop times the area of the loop. Okay, so this loop up here has a certain cross-sectional area. Okay, so the magnitude of the dipole moment is equal to the product of these two things. And to find the direction, what you would do is you can, there are several ways to do this, but the direction is going to be maybe your thumb. We'll say the right hand thumb. And your fingers will curl with the current. Okay, so this is a little bit different than the right hand rule that we use for a cross product. If you come back to this picture that's up here, you can kind of see that for a right-handed person, let's see, their thumb would go that way, and their fingers, I'll just draw three fingers here, would kind of curl around. So the thumb is going to be the dipole moment, and the fingers are curling in the direction of the current, which is in this case it's a counterclockwise current. Okay, so that's how you decide the direction of that dipole vector. Okay, you use your right hand, and it works like that. Okay, so how does this help us? Well, we're now going to redefine the torque, and torque is going to be equal to cross product of mu cross B. And that should look, not crazy, because remember that mu is equal to I times A. And if you have multiple loops of wire, I guess you could have an N out in front times B times the sine of the angle. And so this is actually consistent with the formula that we derived in class for the torque due to a current loop. Except now we've basically replaced I times A with the magnetic dipole moment vector. Okay. So this is a fairly important relationship here. Okay. And let's explore that a little bit more. So let's take it as an example. Let's look at a loop from the side. And let's say that this is an example where the loop itself is running diagonally, and we're looking at it edge on. Okay, so maybe what we would be seeing at the top edge of the loop would be the current coming out, and then down here the current would be going back away from us, back in. Okay, and so I'm not really showing the current running up and down the length of it. Let's say that that loop can pivot right at the center. There's a pivot point there. And let's make the magnetic field vertically upwards. And I'll draw that in several places. Okay, so maybe this is a uniform magnetic field pointing vertically upwards. Okay, so let's do this the old-fashioned way, and let's first figure out if there's going to be, a torque on this loop around the pivot. Let's look at this section of the current down here, the section that's going into the page. So if you use the right-hand rule, current's going into the page, that should give you a force which points to the right. You can check that with the right-hand rule. And then if you look at the current that's coming out of the page, that's going to give you, there's going to be a force on that current which goes to the left. Okay, so basically there is going to be a torque in this case, and if that's your pivot point, and you've got these, a radius here and a radius here, we're talking about a torque which would be counterclockwise. Okay. So that's kind of one way to figure out the direction of the torque, is basically just to sketch kind of the force that acts on the two end segments of your wire. Alright, let's look at it from a dipole moment point of view. From a dipole moment point of view, the dipole moment is going to have to be perpendicular to the plane of the loop. So it's going to have to run this way. And to figure out if it points up or down, you have to use that right-hand rule that we introduced in the last slide. So in this case, using the right-hand rule, you would see that the dipole moment is actually going to go that way. Okay, and you can check that out if you need to take a second and verify that. But that's the direction that it goes. So again, the dipole moment is perpendicular to the plane of the loop. You can see that the dipole moment is not currently lined up with the magnetic field, that there is an angle between these two things. That's the phi angle. And the tendency is going to be that the loop is going to try to rotate to make this vector line up with this vector. And the way that that's going to happen is through, again, a counterclockwise torque. So I'll just draw a little kind of arrow here. So we'll say that mu aligns. So it's going to try to do that. And so the loop will actually twist itself in the counterclockwise direction in order for that to happen. So the nice thing about doing it this way is that you don't really need to know, you don't have to figure out the directions of the forces, but you can quickly determine, if mu is going to line up or not just by looking at where it is with respect to the field. Okay. So phi here, of course, is the angle between mu and b. And again, the torque is going to be the cross product of those two things. You could try that out. If you try the cross product, you point your fingers in the direction of mu. Your palm should face B. So I'll do that on the page here. So my fingers would go, with mu. My palm faces that way, and my thumb is pointing at U, which means that that's a counterclockwise or a positive torque. So the vector symbol for that would be something like that. So again, to use this relationship, torque is equal to the cross product. Now you can use the old-fashioned right-hand rule to predict the direction of the torque if you know these two vectors. Okay. If we made a graph, sometimes it's helpful to graph this out. If you graph torque versus this angle, and you let the angle go from, say, negative 90 degrees to positive 90 degrees, okay, what would that look like? 0 degrees. When it's a 0 degree angle, that would be a situation like this. For 0 degrees, mu and b are lined up, and in that particular situation there is 0 torque. So there's a point right there at 0 degrees. As you go out to 90 degrees, what happens is that mu begins to turn this way, but b is still going up that way. So this would be for positive B's. And the tendency is for the torque to be positive because you're going to get a counterclockwise turn. And so that is going to be something like this, going up to some maximum value. Okay. And if you go to negative 90 degrees, now mu is going the other way, and the tendency is to rotate clockwise. So that's a negative phi angle. And that's going down like so. Okay, so this is actually, what is this? This is a sine function, right? And it better be a sine function because we know that the magnitude of this is going to be equal to mu b sine of phi. And so that sine function, is not an accident. It's not a coincidence. It's because of the way we've defined things. Okay. So that is that. And these maximum and minimum values, of course, would be I times A times B, and negative I times A times B. So again, the tendency of mu is always to align with the external field. That's what it's always trying to do. Okay, and then one last thing on this potential energy. And with potential energy, the question would be, when do you store the most amount of energy, in the loop, when it's in this field? Are you storing energy when the loop is aligned with the field, or are you storing energy when it's not aligned? And the answer is that you store the energy when it is not aligned with the field, because it's always trying to kind of get back to alignment. Okay, so let's try to be more specific about this. Talk about the work by the field. We're talking about rotation here, so work isn't going to be force times distance, but it's going to be torque times angular displacement. Okay, so the work that's done by the magnetic field on rotating this loop is going to be torque times the angular displacement. Let's substitute into that. That's torque is going to be equal to mu times B times the sine of the angle. Of course, mu times b is a constant. That just comes out. So you've got mu b sine of the angle. And when you take the integral of that, of course, that just becomes cosine. Okay. So this is the work that's done by the field. It's the dipole moment times the field times the cosine of the angle. We know that the change in energy is always going to be the opposite of this work. So that's going to tack a negative sign on there. And oftentimes what we just say instead of saying delta U is we'll just say that the potential energy is equal to that, because we assume that the initial potential energy, is equal to 0. So this is how you find the potential energy that's stored. You might notice that this is a product of two vectors times a cosine. That's actually a dot product. So the most compact way of writing this is actually just like that. And that's kind of gives you the idea of potential energy. So what would this look like if you were to graph it, and would that make sense? Let's end with that. So we've got potential energy here. We'll have the angle here. Let's make this 0 degrees. Let's go from 0 to 180. Okay. And what does that mean? Well, at 0 degrees, that means that your two vectors are aligned perfectly. At 180, your two vectors are going to be opposite. Okay. And for 90 degrees, that's going to be kind of when it's midway, so your perpendicular vectors. So I guess B is always pointing up. Mu is the thing that's changing direction here. So on a graph, this is going to look like the negative cosine function. Okay. And the reason, of course, is because we just derived that, right? We said that the potential energy U is equal to negative mu dot B. So, okay, it's a negative cosine function. But also think about the physics of this, that when the two vectors are lined up with each other, that's a minimum in the potential energy. So when you have alignment, then the U is a minimum, which it is. Okay. And when you have counter alignment or anti-alignment, when the two vectors are completely flipped, that's when you have the most potential energy, because as soon as the ring starts to flip, it's going to convert that stored energy into kinetic energy, and it's going to accelerate as it does so. Okay, so when these things are anti-aligned, that's when you have the maximum potential energy. And when you're at 90 degrees, you're somewhere in between. Okay, so just the potential energy from an energy point of view, you can quickly tell, what type of energy situation you have, if you know the direction of the dipole vector and you know the direction of the magnetic field. And from what we said earlier in the lesson, you can also figure out which way the loop itself is going to turn. If it's going to turn clockwise or counterclockwise. Okay. So that is just kind of the summary of the dipole moment physics. Of course, you can feel free to look in your textbook. They give probably a more formal derivation of these things and a more detailed explanation. But I figured this would be a good way to just introduce you to the concept, and it should help you with the homework that you're working on. Okay, we'll talk soon.